Hi everyone, I'm Florent BICKERT. I'm a third-year PhD student in the LHEEA lab, and today I would like to speak about the effect of wind propulsion on the steady-state balance of a merchant ship. Before starting, I introduce an acronym I'm going to use a lot, which is WPS, which stands for Wind Propulsion Systems. So when a ship is fitted with a wind propulsion system, this system generates a thrust force, which is wanted, of course, but also a side force. And to compensate the side force, the hull drifts, which allow to generate an hydrodynamic side force in the opposite direction. And this side force comes at the cost of an additional resistance, the so-called sail-induced resistance, which reduces the wind propulsion thrust. And also the fact the ship is drifting generates a leeway angle and a rudder angle, which affects maneuverability. And the last point is the fact that because of the high lever arm of the wind propulsion center of effort, this generates heel. And the increase in heel angle affects stability. So that is why we need to evaluate precisely how the wind propulsion system impacts the ship's behavior. So what affects the ship's response to a wind propulsion force? Well, first, we're going to consider only the side force because it has been proved that the ship's drifting behavior is mainly due to the wind propulsion side force. So the thrust force has an effect, especially the fact that it reduces the propeller thrust, and so it reduces the inflow velocity at the rudder location, which will generate higher rudder angle. But the main contributor to the ship's drifting behavior is the side force generated by the wind propulsion system. So what are the parameters that are impacting the ship response? First, you have, of course, the hull form and the rudder form, the propeller form also. And then what kind of wind propulsion technology we're talking about. So rotor sails, wing sails, suction wings, whatever, kites, soft sails. And then shift speed and the route will define the encounter weather and especially the encounter angle of attack and of the wind. So apparent wind speed, apparent wind angle. So if the first point, the hull and rudder form are ship dependent, the other one are more case dependent. It means that it depends a lot on what kind of wind propulsion technology we're using, what is the route, what is the ship, which makes it difficult to take results that were obtained with one particular ship on one particular route with one particular wind propulsion system and to use them for another ship for another wind propulsion system. So that is why what one could wonder how to evaluate the ship response independently from the wind propulsion system. And that is what I would like to study today. So that is why we are going to look at a technology agnostic approach that was proposed by Kramer and Steen in 2022, where they studied, they defined a method which is independent from the wind propulsion system. And they applied it to a 120-meter long tramper that was studied with a 3 degrees of freedom maneuvering model. However, Van der Kolk in 2020, during his PhD thesis, where he showed that the high vertical lever arm of the wind propulsion system impacts a lot not only the fact that the ship is heeling, but also it impacts the maneuvering motion. So the heel should be taken into account in the maneuvering model. So that is why in the present work, I would like to reapply the methodology by Kramer and Steen to a more common hull design than their 120-meter long tramper of their own design, and while considering the effect of heel on the results. So this is the plan of the rest of the presentation. I'm going to briefly introduce the method, give some results at design speed for the 2 ships investigated, then study the effect of a speed reduction, compare the result with those from Kramer and Steen, and then I will propose a side force evaluation before concluding. So for this case study, we're using the power prediction program which is developed in the LHEEA and which is open source, XWASP-CN. And we're studying two academic ships that were widely studied in the literature, supertanker, capsized supertanker, the KVLCC-2, and a 230-meter long container ship. And so because of the low transverse stability of the KCS, we are going to take into account LHEEA, as I already said. So we're looking only at the steady state calculation, which means that the sum of forces are, and the sum of the moments are 0, and we impose the ship speed. And then we consider only 4 degrees of freedom. We neglect trim and sink. So it leaves us with 4 following unknowns: the leeway angle, which just appear on the figure. And then you have the rudder angle for the yaw balance, the heel angle for the heel balance, of course. And then we have the propeller RPM, which is used to balance the longitudinal equation, but that will not be used further in this study. Then regarding the forces, so as already said, we applied a constant aerodynamic side force at midship, 30 meters above deck. And regarding the aerodynamic forces, so for the hull, the propeller, and the rudder, we consider the MMG model, which is the famous maneuvering model, which is system-based and which has a physical description of the interaction between the hull, the propeller, and the rudder. And it has already been validated for both ships. Then we introduced 2 dimensionless parameters. The first one is the side force ratio. It's the ratio between the side force which is applied, the aerodynamic side force, and the calm water resistance of the ship without any perturbation. And we consider a side force ratio between 0 and 2 based on the work by Kramer and Steen in 2022. And the sail-induced resistance, well, it has this, it reads this equation, but basically it's the added resistance due to the fact the ship is drifting. And finally, we consider 3 types of simulation. The first one is 3 degrees of freedom, so we neglect heel. The second one is 3 plus 1. It means that we compute heel, but it does not affect the other motions. And the third one is the 4 degrees of freedom approach, where the heel is computed and is affecting the other motion, especially the hull forces. Well, I think I don't have, well, yeah, maybe let's spend a bit of time on this. So yeah, we have the unknowns, which are the 4 quantities I already described. And this is how the power prediction program is working. So basically we define values for the unknowns, we compute the force, we verify if the steady state balance is respected. If it's not the case, we iterate until we respect it. And when the sum of forces are 0, then we can compute the sail-induced resistance. So let's have a look at the first results. So for the supertanker at its design speed, which is 15.5 knots, you can see from left to right sail-induced resistance, heel angle, leeway angle, and rudder angle as a function of the side force ratio. And basically we see that the higher the side force ratio, the larger all these quantities are, which is expected, of course. And another point is that the heel angle is quite small, even when you apply a side force which is twice the calm water resistance. It's less than 1 degree. This justifies the fact that 3-Dorf approach is sufficient. I forgot to mention that I'm not showing 4-Dorf curve for the ship because I couldn't find any roll coefficients for this ship, and that's explained by the fact it's useless because the ship is basically not heeling. But if we look at the results of the KCS, the container ship at 20 knots, well, we can see that passing from 3 degrees of freedom to 4 degrees of freedom changes a lot the results. It doubles the sail-induced resistance. It makes the rudder angle and the heel angle quite high. So that justifies the fact that the 4-Dorf approach is necessary. We have to say that from an operational point of view, such values for heel angle and rudder angles are unrealistic. I mean, you cannot have heel angles of more than 5 degrees. It can be even less depending on the ship type. And for the rudder angles, having more than 10 degrees. Oh, j'ai rien fait. And yeah, for the rudder angle, having more than 10 degrees is quite critical from a maneuvering point of view. So we see that it's important to study not only the additional resistance we get when we add a wind propulsion system on the ship, but also the rudder angle and the heel angle, because it's really important to know if the ship is pushed beyond its operational limits or not. However, as you can wonder, 20 knots, a ship sailing at 20 knots with a wind propulsion system is very unlikely to happen. Most of the time, the wind-powered ships are sailing at smaller wind velocities, smaller velocities, sorry, in order to open the apparent wind angle. So that is why we're going to study the effect of a speed reduction. So for the supertanker, let's have a look at the impact of 25% speed reduction, so passing from 15.5 to 12 knots. Basically, it's not affecting the results. I have to say that, of course, since we changed the ship speed, we also changed the calm water resistance. So the side force ratio is changed also. But if we look at the results for the KCS, it does change the result. It makes them more acceptable from an operational point of view, even if we still have very high values. So let's have a look at a comparison between these results and those from Kramer and Steen. You can see on this figure the LHEEA ship that they studied, which is the one below. And so it's much smaller, and it was studied at 3 degrees of freedom. So that is why I removed the heel graph. And we can see that the sail-induced resistance is higher. The leeway angle is double that of the KCS and the KVLCC, whatever the side force ratio. And the rudder angle is similar to that of the supertanker. But let's now have a look at the distribution of forces. So on the left, you have the normalized hydrodynamic side force, and on the right, you have the sail-induced resistance, normalized also. In blue, the hull contribution. In orange, the rudder contribution. What can be seen is that globally, for all three ships, the side force, the hull contributes to 50% of the side force, approximately, while it's only 5 to 6% of the sail-induced resistance for the first two ships, the KVLCC2 and the KCS, but 27% for the Tramper. So the first thing we can see is that the hull is much more efficient than the rudder at generating side force. And the second thing is that the KVLCC2 and the KCS that were designed to be representative of existing ships are actually more efficient than the Tramper's hull, which is designed by the two researchers that did the publication. So now, of course, we all want to know where are we on the curve, because if we only have small side force ratio, well, basically this study is showing that it does not impact a lot the ship. So in order to do so, even if the main point of this methodology is to be technology agnostic, if we want to have an order of magnitude, we have to choose a technology and we have to take wind data. So in order to do so, I decided to use a rotor sail model because it's the most sold technology as of today. And the largest rotor sail that we have on the market is 35 meter high with a 5 meter diameter and with an upper end plate, sorry. Well, I'm not going to go into details about how we modeled it, but we did it with another open source simulation tool that we have at the lab and that we're developing, CN Aero Models, which is using nonlinear lifting line theory. And I will give you a reference to paper after if you want some more information about how we did it. But just know that we validated it against full scale and wind tunnel measurements, and that the RPM is selected to maximize the RPM of the spin velocity of the rotor is always chosen to maximize the ship propulsive thrust power, taking into account the fact that you need some energy to spin the rotor. So we perform a statistic evaluation of the forces. In order to do so, we compute the propulsive the rotor thrust and the rotor side force through varying true wind speed and true wind angle, and then we multiply these forces with the global wind matrix from the International Maritime Organization. And well, if you look at, I have a pointer. Yeah, if you look at here, this is the thrust ratio, and here the side force ratio. Well, basically, it's peanuts. We can see that the thrust force ratio is the mean thrust force ratio is from 0.01 to 0.04, whatever the ship and the ship speed, and the side force ratio is going from 0.04 to 0.12. So basically, it shows that these ships are not affected by one rotor sail. But what happens if we consider several rotor sails, and if we don't look at the mean value, but if we look at the probabilistic density, and where we can see that whatever the number of rotors and for both ships, we decided to test 5 rotors for the KVLCC2 and 4 rotors with the KCS. We neglected the interactions between the rotors just to have an order of magnitude. And you can see that the probability to have a side force ratio greater than 1 is only 2% for the KVLCC2 with 5 rotors and 10% for the KCS with 4 rotors. So the side force is not really affecting these ships. So as a conclusion, we have a simple and technology agnostic method for evaluating the drifting ability of a ship that we applied on 2 ships. We've seen that it's important to consider heel angle, especially for a low stability ship. We've seen that the supertanker is less impact than the KCS, than the container ship, and that the rudder is the main contributor to the sail-induced resistance. I'd like to say also that the sail-induced resistance should not be studied alone. It's important to consider also the rudder and the heel angles in order to be sure that the ship is not pushed beyond its operational limits. Reducing ship speed is, of course, reducing all these quantities. And if we do an evaluation with realistic wind propulsion technology, such as a 35-meter high rotor sail, using the IMO wind matrix, where we see that the side force is actually negligible for these ships, even when considering several rotors. So my future work will deal with the effect of reducing ship's size and the fact that when you reduce ship size, then it changes a lot the conclusion. The side force is really not negligible. And then we can study the effect of adding hydrodynamic appendages to reduce the sail-induced resistance. If you want more information about these results, you can have a look at the publication that was published 2 days ago in the Journal of Sailing Technology. Thank you for your attention.